In today's fast-moving space industry, technology is not just helping us explore new places, it is changing how we work with the machines that keep astronauts safe. As missions get longer and more complex, clear and easy communication with onboard systems is more important than ever. Old controls like keyboards, switches, and touch screens still work, but they can be hard to use in space. Imagine trying to tap a screen while floating or reach a switch when you are strapped in tightly. This is why multimodal human-computer interaction is so important. It uses different ways for astronauts to control systems like voice commands, hand gestures, eye movements, facial expressions, and even body signals. This makes it easier to work with machines, even when hands are busy or movement is limited. For example, an astronaut who cannot move much during re-entry can still operate important systems by moving their eyes or speaking. Or think about robots on the ISS that can understand both voice commands and hand gestures to help astronauts fix equipment. These systems also make life in space less stressful and more comfortable. This is very important no long trips to the moon or Mars, where mental health is just as important as physical health. In the future, multimodal HCI will be at the center of new space habitats, lunar bases, and missions to other planets. This is already changing how we design spacecraft and build AI helpers, making space travel safer and more human-friendly. In this video, we will look at real examples of this technology and see how it is helping shape the future of space travel, not as science fiction, but as the next big step in our journey to the stars.
When we think of human-computer interaction, we picture touchscreens, keyboards, or maybe voice assistants like Alexa. But in space, it's a completely different story. Everything changes because the environment is unlike anything we experience here on Earth. First, there are the physical constraints. Astronauts float in microgravity, meaning they can stand still, lean over a console, or easily press a button. They are often wearing bulky clothes, and even small hand movements can be tricky. That makes traditional input methods like keyboards or knobs almost useless. So, we need some smarter, more adaptive interfaces. But it's just about movement. It's also about the mind. Space missions are high stress, high risk. Astronauts manage dozens of tasks at once. Monitoring life support, navigating, repairing systems, sometimes all within minutes. So, interfaces have to be simple, intuitive, and fail proof, even in high pressure situations. Another big challenge communication. On deep space missions like to Mars, there is up to a 20 minutes delay in messages between Earth and the spacecraft.
As you know, on a SpaceX Crew Dragon, or Dragon Freedom, we also, while we've been up here, we had the Boeing OFT mission successfully dock a Starliner. So we got both of those in rotation. We also have the Soyuz as well, getting people up here to the ISS.
That means astronauts can't just call mission control when something goes wrong. They need interfaces that guide them in real time and let them act autonomously without waiting for help. Want a real example? A great example of these challenges is the Apollo 11 lunar landing. As Neil Armstrong was manually piloting the lunar module, Just minutes before touchdown, alarms started going off right in the final descent. The guidance computer was overloaded. In that intensive moment, the interfaces had to deliver only the most critical information, quickly, clearly, and without distractions. Armstrong had to rely on his training and trust in the system to stay calm. In space, human computer interaction isn't just a convenience, it's the lifeline. The environment is unforgiving, and when something goes wrong, astronauts don't have time to search through the complicated menus or wait for help from Earth. That's why well designed interfaces must support the human, not other way. In the end, it's about keeping humans safe, millions of miles from home.
When we think about using computers, we usually think of one way to give commands like typing or touching a screen. But in space, using only one method can be risky. That's where multimodal HCI comes in. Multimodal HCI means using many ways to give and receive commands at the same time. For example, astronauts can use voice, touch, eye movements, or even brain signals. This makes systems easier to use, more flexible, and safer. Now we want to take a look at some main ways astronauts can give commands. The most common way is voice control. Astronauts can say things like open airlock or turn on lights. It is fast and lets them keep their hands free. But if it's too noisy or the microphone breaks, it won't work well. Next method is touch. Astronauts can also use buttons, switches, or touch screens. This is quick and simple. But in a space, they often wear thick gloves, or their hands may be busy or hurt. So touch can be hard to use. We also have eye tracking modality. With eye tracking, astronauts move a cursor or pick options by looking at them. They can then confirm by blinking or saying a word. It works well when hands are busy, but it can be tiring and may not work if the head moves too much. As first modality, we want to mention gestures. Gesture control uses cameras to watch hand or arm movements. Brain Computer Interface, BCI, is also a modality that researchers want to represent, maybe in future. BCI reads brain signals and turns them into commands. This is still new and not fully ready yet, but it could help when an astronaut cannot move at all.
So far, we have explored what multimodal human computer interaction is and how astronauts can use different ways to communicate with machines. But the real question is, where does all this actually get used in space missions? Let's take a look at real world applications inside spacecraft, during spacewalks, and even on planetary surfaces. Inside the spacecraft, things can get pretty intense. Panels, switches, touchscreen displays, all tightly packed. In an emergency, every second counts. Finding the right control fast can mean the difference between success and disaster. That's why engineers are building smarter cockpit systems. Picture this: an astronaut simply looks at a control on the panel, then says, activate oxygen system. Eye tracking plus voice command. Faster, hands free, and perfect for when gloves get in the way or hands are busy. Now imagine a medical emergency. Astronauts aren't trained surgeons. but space doesn't wait. With augmented reality headsets, like the Microsoft HoloLens, astronauts can follow 3D instructions floating in front of them, guided in real time by doctors on Earth. It's like having a virtual assistant walk you through a life-saving procedure. Now let's head outside the spacecraft. During the spacewalk or EVA, imagine trying to control a computer while floating. With thick gloves and limited vision. Into gesture controlled drones. Astronauts can simply move their arm or hand to signal a drone to fly over, check a module, or deliver a tool. No buttons, no joysticks. Smart space suits are also evolving with wearable tech like smart gloves that sense finger movement or helmet displays that show status info right inside the visor. Astronauts stay informed and in control without having to look away or stop what they are doing. Now picture this. You are on the surface of Mars. Red dust, rough terrain, and heavy equipment. You need to assemble a habitat or fix a critical system. Multimodal HCI makes it easier. With AR headsets, astronauts can see step-by-step construction overlays like a virtual guide showing where every part goes. For over missions, astronauts can use a mix of gestures, voice, and gaze. For example, just point to the distant rock and say, "Go there." The rover gets it. It's natural, intuitive, and works even in big, clunky gloves. All of these use cases rely on a powerful combination of advanced technologies, sensors like cameras, microphones, eye trackers, and EMG or EEG systems to detect gestures, speech, gaze, and even brain activity. AI and machine learning to enable context aware interactions that understand astronauts' intentions and adapt to the changing conditions. Wearables such as smart gloves, AR glasses, and haptic vests provide feedback and control options directly on the body. Interfaces including virtual panels and 3D gesture zones, which replace or complement traditional buttons and screens. By combining these cutting edge tools and multimodal interaction methods, astronauts can work more safely, efficiently, and confidently, no matter where they are in space. From piloting spacecraft and performing medical procedures to exploring distant planets. Multimodal HCI is redefining how humans and machines collaborate beyond the Earth.
Well, at this part, we want to talk about researches and future works. Now that we've explored the importance of human computer interaction in space and how multimodal systems work, let's take a look at the current researches happening today and where these technologies are heading in the future. Well, today, many new projects are pushing the limits of multimodal HCI in space. NASA and the European Space Agency, ESA, are leading programs to help astronauts work better and more independently. One famous project is called Spheres. These are small, free-floating robot satellites inside the International Space Station, or ISS. They are used to test navigation, self-control, and new ways for astronauts to give commands like using voice and gestures. Another big project is Project Sidekick, which uses Microsoft's HoloLens headset in space. With this headset, astronauts can see digital instructions over the real world around them. They get a step-by-step help and can also talk and show things to mission control on Earth. By using voice and hand gestures, they don't need to look at paper manuals and can keep their hands free. This makes work faster and helps reduce mistakes, especially during repairs or emergencies. Universities are also helping develop new multimodal HCI systems. At MIT Media Lab, researchers are creating systems that use voice, eye movements, touch, and even facial expressions together. Stanford University and other labs are working on interfaces that adjust automatically based on the astronaut's situation and stress level. Many of these tests happen in fake moon or Mars bases on Earth. These analog habitats copy things like low gravity, small spaces, and mental challenges. They help researchers test and improve new interactions methods in realistic settings.
Rapid, controllable, and repeatable test environment. And that's really one of the beauties of virtual reality is that not only can we recreate anything digitally and add the different tools and functions and widgets and heads-up displays and whatever else we might need, but we can actually drop somebody right there on the surface of the moon, of Mars, and see how they perform in the actual environment.
In the future, HCI systems in space will become even smarter and more flexible. One exciting idea is to make systems that learn from each astronaut's behavior and change in real time. For example, these systems might make controls simpler during stressful times, show important info first, or switch from voice to eye control if needed. Another promising area is brain-computer interfaces, or BCIs. BCIs read signals from the brain to control systems using only thoughts. This is still in early stages, but it might help in deep space, especially if physical controls are broken or cannot be reached. Future Moon or Mars bases will also use fully immersive interfaces. By combining virtual reality, augmented reality, and 3D computing, astronauts can interact with systems in a more natural way. Imagine walking through a virtual map of a base, checking machines with floating instructions, or talking to an AI assistant that gives real-time help, even when talking to Earth takes too long. Multimodal HCI will also help with planning missions and fixing equipment. Systems can guide astronauts step by step, watching their voice, eyes, and hands to help them finish difficult repairs. In short, multimodal HCI is not just about cool gadgets. It helps astronauts stay safe, confident, and efficient in space. From floating robots and AR headsets to mind control systems. These new tools are changing the future of space travel and making new things possible for humans far from Earth.
Let's explore some of the major challenges and limitations engineers face when designing multimodal human-computer interaction systems for space. In extreme and unpredictable conditions, these systems must be reliable, efficient, and above all, safe. Space is brutal. Temperatures swing from 120 Celsius in sunlight to minus 150 Celsius in shadow. These extremes can cause touchscreens to freeze, sensors to glitch, or even completely fail. And it's not just the heat and cold. Cosmic radiation can corrupt data or degrade sensitive systems, like speech recognition or brain computer interfaces. In microgravity, gestures behave differently. Arms float, bodies drift, which affect how motions are detected. Even voice commands get tricky. Helmet echoes, machinery hum, and life support noise can all interfere with speech recognition. Over time, optical systems wear out, dust builds up, and radiation damage accumulates, making long term reliability a major challenge. In space, every gram and every watt counts. Spacecraft and suits have strict size, weight, and energy limits. Every added sensor, screen, or processor uses valuable space and brain power. That's why engineers must design compact, lightweight, and low power systems that won't overload the ship's infrastructure. Efficiency isn't just a design goal, it's a requirement for survival. Multimodal HCR introduces new ways of interacting. Voice, eye tracking, gestures, even brain signals. But astronauts don't just pick it up. They need extensive training, often using AR/VR simulators to practice these new systems under mission like conditions. And in high stakes moments, muscles memory matters. The interfaces must feel familiar and intuitive, or it risks slowing them down instead of helping. Here's a tricky one: input confusion. Imagine an astronaut says, "Start diagnostics," while accidentally making a gestures that means something else. Which command should the system follow? Multimodal HCI must be smart enough to detect, prioritize, or ask for confirmation without frustrating the user. That requires robust AI, context awareness, and smart error handling, all running in real time. These challenges highlight that multimodal SCI in space is not just about improving convenience. Is it vital for astronaut safety, mission success, and operational resilience in one of the most extreme environments imaginable?
As we've seen, multimodal human-computer interaction is not just a technological luxury, it's an absolute necessity for the future of space exploration. From the extreme challenges of microgravity, temperature swings, and radiation, to the need for intuitive, hands-free control under high stress and communication delays. By combining voice, gesture, eye tracking, touch, and even brain-computer interfaces, these systems offer redundancy, adaptability, and reliability that traditional single-mode controls simply can't match. Current research programs by NASA, ESA, and leading universities are pushing the boundaries to develop smarter, more intelligent interfaces that respond to astronauts' needs in real time, whether on the International Space Station, lunar habitats, or Mars missions yet to come. As we step into this new era of space exploration, the importance of multimodal HCI extends beyond astronauts. It's a call to innovators, researchers, and students around the world to join in shaping the future of how humans and machines collaborate in the most extreme environments. If you're inspired by this incredible field, consider diving deeper into researches, developing new interface technologies, or exploring educational paths in human-computer interaction, space science, and engineering. Together, we can build the systems that will take humanity farther than ever before.